are in Introduction to Statistical Learning. We're in Chapter 5, in which we are discussing topics like bootstrapping. Okay, here's the question. So we'll go through it in parts here, but they all are based on this premise here, so I'll read that. So we will now derive the probability that a given observation is part of a bootstrap sample. Suppose that we obtain a bootstrap sample from a set of n observations. And then we're going to answer a bunch of questions here. So let's go through those. Okay, so part A is, what is the probability that the first bootstrap observation is not the jth observation from the original sample? Justify your answer. Okay, so in other words, we have our sample data, and we're going to start bootstrapping. And so we're going to pull one of the observations to put into our bootstrap sample. Okay? And we want to know the probability that drawn sample, that drawn observation, is not the jth observation, where j can be any one of the observations in the original sample. Okay. So again, we have n observations. And the probability that any single draw for our bootstrap sample will be the jth observation is just 1 over n, right? So if I have, 5 observations in my original sample, well, now I'm going to go through and I'm going to sample that my set of observations for the bootstrap. And each of my n observations has an equal probability of being drawn. So they all have 1 over n probability of being drawn on any particular draw. So now the jth observation, so we're going to draw once for the bootstrap, and we're looking at just one of the observations. Okay, so the probability that the jth observation is drawn for this particular draw of the bootstrap is 1 over n. That means that the probability that it is not drawn is 1 minus 1 over n. Okay. Part B. What is the probability that the second bootstrap observation is not the jth observation? Okay. Well, so this is just like the first question, part A, but now instead of the first draw for our bootstrap sample, we're looking at the second draw. Okay. But when we're doing a bootstrap sample, after I draw an observation to put into the bootstrap sample, it is just put back in the pool of potentials that I could draw on the next time. That means that every time I'm drawing, every observation has a 1 in n chance probability, a 1 in n probability of being drawn for the bootstrap. Okay, so every draw for the bootstrap has the same probability of not being drawn, 1 over n, right? So the answers are the same, and it's because we are sampling our set of observations with replacement. Okay. Part C. Argue that the probability that the jth observation is not the bootstrap sample. I missed a word there. Argue that the probability that the jth observation is not in the bootstrap sample is this right here. Okay. So in other words, we create a bootstrap sample that has n draws. Okay, and we want to know the probability that the jth observation from the data is not in that bootstrap sample. Okay, and it tells us that this is that probability, and so we want to somehow derive that or justify why this might be the case. Okay, well, we've already seen then that the probability for any particular draw that j is not drawn is this. It's 1 over n. Okay, but now we have to repeat that n times. Okay, so we need to multiply this by itself n times. Okay, and so when we do that, we get the expression that we were asked to defend. Okay. All right. So now parts D through F are really the same. So when n equals 5, that's part D. 100, that's E, or 10,000, or maybe it's supposed to be 100,000. I can't remember. Doesn't matter. I mean, it does matter for the number, but the process is going to be the same. When n is these values, what is the probability that the jth observation is in the bootstrap sample? Okay. All right. So again, we're building off of the previous set of questions. Okay. So for any value of n, whether it's 1, 2, 5, 100, 1,000, 10,000, whatever, we already know what the probability that the jth observation is not contained in that sample, right? It's what we just found. It's this. Okay. So that means that the probability that j is in the sample is just simply 1 minus this guy. Okay. So this becomes our expression, right? It's 1 minus the probability that j is not in the sample. Okay. It's just the complement of not being in the sample. And so we can go through, we can plug in into this sample right here. Okay, and so these are the values, and I've just done this in some R code, so I have n of 5, 100, 10,000, and then I'm just putting that expression into there, right? And so I run this, and I get these values. For n equals 5, it's 67.23%. Then it's 63.40% for n equals 100, and 63.21 for 10,000. Okay. I'm actually going to drill down a little bit further into this question, even though it's not asked for. Okay. So what we've just seen is the probability that j, the observation j, is contained in our bootstrap sample, okay, at all. But remember, every time that we make a draw from our data, we put that observation back in the pool of things that can be drawn again. So any observation can be drawn more than once. In fact, it can be drawn up to n times, right? Because I'm making n draws, and the jth observation is available for all n draws. Okay. So this means then that the number of times that I draw observation j, and let's call that xj, is a binomial random variable, right? With n draws, where each draw has a probability of drawing j 1 over n times. Okay, so the number of times that j is drawn for a sample of size n, for a bootstrap sample of size n, is distributed like this. Okay, and so that means that I can find the probability of drawing j, observation j, k times is the probability that x, the number of times I draw j, equals k, is just equal to this expression right here. All right. So let's look at what this would be for n equals 10. Okay, so I have 10 samples. Okay, and I'm going to draw the jth observation. Oh, you know what? I should actually have 0 in there, shouldn't I? Because I can draw it 0 times. Okay. And so I'm going to draw j anywhere from 0 to 10 times. Okay, and so to do that, I'm going to put all of that. Don't look at this plot; it's actually incorrect because I forgot to put 0 in there. So let me actually clear that output. Okay, so I'm going to create a data frame where I have k, the number of times I'm drawing j. Okay, and it's just going to be x, right? A value between 0 and n, and then a probability of drawing that, which is just d binom. So this expression right here is doing this. Okay, and so it's going to give me the probability of drawing drawing observation j k times out of n tries. Okay, so now let me plot that. Okay, so the way that we read this is we say that the probability of drawing of j being in our sample 0 times is about 0.35 or so, and then about 0.4 for once, about 0.2 for twice. Okay, and we could get the exact values actually if we just looked at the data frame, right? So the probability of it being 0 is about 35%. The probability of it being 4 times is about 1%. Okay, yeah, which makes sense. Okay. So we can even go further and we can say, okay, what is the expected number of times that we expect j to be in our sample of size n? In other words, what is the expectation of x? And we can also find the variance of x. Okay. So for a binomial variable, the expectation is n times p, and here n is n, and p, the probability of the event, is 1 over n, and so this just equals 1. So this means that that the expected number of times that any particular observation j, is included in our sample, our bootstrap sample of size n, is always 1. Now, of course, that doesn't mean that it is always 1. There's some variance around that. And how do we find the variance? Well, we find the variance like this. So the variance for a binomial distribution is np times 1 minus p. Okay. So so when we kind of go through all this, so the np we've already found, and that's just 1. Okay. And 1 times what's in parentheses is just this guy right here. So that's the variance then of how many times we expect to find observation j in our sample, right? So if n equals 10, then the variance is 9/10. Okay, part G. So we're going to create a plot that displays, well, I'll just leave those up there. Create a plot that displays for each integer value of n from 1 to 100,000 the probability that the jth observation in the bootstraps, that the jth observation is in the bootstrap sample. Comment on what you observe. Okay, so I have sample sizes of 1 to 100,000, and I'm calculating the probability that observation j is in that sample, just like we did above. Okay, so I have a vector called n and a vector called p any. Okay, and then I'm going to plot these. Okay, so I'm plotting the probability of observation j being in our sample over the size of the sample. And what we get is this, and that's not very pretty. So in the second one, I'm actually taking the log of n just to kind of get a prettier picture. Okay, and so when I do that, I get this. Okay, so in other words, as the sample size increases, the probability that the jth observation is included in the sample looks like this. And notice that it kind of asymptotes at this line right here, and we're going to find that that line is about 0.63. Okay, how do we know that it's 0.63? Okay, well, the way that, not that the question is asking for this, but we could find this because if we were to take the limit if we were to take the limit of this, okay, so what is this? If we were to take the limit of this right here, okay, which is the probability of not being in the sample. Okay, so I'm omitting that lead 1 there for a reason. Okay, so this expression right here is 1 over e. Okay, and I'm not going to derive that here, but this is what it is. Okay, and so if I wanted the limit then of the probability that the jth observation is in the sample, then I would need to take this expression and find the limit. Well, that is just 1 minus 1 over e. Okay, and remember the constant e is about 2.71, but it's it just continues on forever. So so this is 1 minus 0.37, which is about 0.63. So in other words, as n approaches infinity, we expect the probability that the jth observation is in the sample to be about 63%. Okay. And now, in the final part, part H, we'll investigate numerically the probability that a bootstrap sample with size equals 100 contains the jth observation, where here j is 4. Okay, so we're gonna create a bootstrap repeatedly. Okay, so we're gonna make many bootstrap samples and record whether the fourth observation is in the sample, and it gives us the code to do that. Okay, and so I'm just going to run that code. Well, actually, I've already done it, and you see that the average probability that the fourth observation is in there is 0.6379 in this particular sample set of samples that we're generating. We can do this a few times, and you can see it just kind of hovers around 0.63. Okay, well, that is what we found analytically to be the limit as n approaches infinity. Okay, we'll call that good here.